since I won't see anything myself, I need to. Wow. Okay. So last time, we have started the topic that is called limit and calling. Today we will continue. Let's remind a couple of definitions from the last lecture. So first of all, I have from category J to category A here be a function, and J is a small category. Then, yes, and we have object A belonging to A. It's just object. That definition was the following. A natural transformation from the functor delta sub A to functor F, let's call it alpha, is called a comb over F. When we will unravel this definition, we'll see the following. That for any yes. Okay, before going to that, let's then remind where delta sub A is a functor from category J to category A that factors through the trivial category. So first we go to a trivial category with one object, one morphism. It's a unique functor, that's why I'm writing string, and then any functor from a trivial category to category A picks up with precisely an object. And their composition is called delta A. So it takes every object from category J to category A and every morphism in category J to the identity morphism on object A. Okay. Then for any morphism from X to X prime F in J, we have the following diagram. It's a diagram of natural transformation for our morphism F. We will have delta A X going to delta A, right? Here is delta A of F going down here. It will be F of X, F of X prime. Here is F of X. This curve here is alpha sub X. This is alpha sub X prime. Okay, that's a definition of natural transformation. But alpha sub X, alpha sub A of X, and of X prime are objects A by the definition of the constant function. And the morphism is identity on A. Therefore, we can write this diagram in the following way. We have A going to F of X, F of X prime, F of F, alpha X, alpha X prime. And this triangle commutes for every f. This is usual definition of a cone that you can see in any book on the internet, wherever you are looking. You have a cone whose sides are the morphisms from fixed object to the diagram, and the tip of the cone is fixed, it's object A. You can always think about it a little more geometrically. Here is your F image of category J, F of J. Here is object A, and you have down looking arrows. They are precisely elements. That's why it's called cone. But from a category, from a point of view of category theory, to look alpha as a natural transformation is much more beneficial. It can give us the precise feeling what is the limit that we are looking for. So the limit will be the closest cone to this base diagram, so that every cone will factor through. Okay, then let's talk about what is factor. So part two. Any morphism from A to A prime, let's call it H in A, induces a natural transformation, delta sub A to delta sub A prime, delta F. This is a straightforward thing. So this functor picks up A, this functor picks up A prime. Both they are constant on every morphism in category J, and delta sub F is F on every component. Just write down this thing, and you will see that here will be F, F, here A prime, and here identity.
So where you wrote H should be F, right?
H. Right.
Oh.
Therefore, if delta sub A prime natural transformation to F, let's call alpha is a cone, then delta sub A to F, which is a composition alpha with delta sub H, also cone, also a cone. So we can move from one cone to another cone. How does this look? This looks as we have delta sub A, delta A prime, here is F, here is natural transformation alpha, here is natural transformation delta sub H, here is their composition. Alpha, composition, delta sub H. Okay, therefore, we can consider the following facts. Cone form a cone form a category. This will be category delta, comma F, where functor delta is going from category A to category of functors from J to A. So this functor takes every object to a constant functor on diagram diagram J. And here we have a functor from a trivial category, which picks up the unique functor f in our functor category. So here is our span that we use for comma categories. So category of columns is delta comma f. Again, I emphasize even f is a functor, but it's a constant. It's an object of a functor category. So actually this things varies here, and this is fixed. So all our arrows in comma category have fixed and in f. An object in the beginning varies. Any questions? Okay. Then I will give a definition. A limit of f is a terminal object of comma category delta comma f. This terminal object as a cone sometimes is referred to as a universal cone. We can look at this in the following way. That we have a diagram f of j. Here is our terminal object. This terminal object will be called lim f. Here is our lim f. This object. We are taking any other cone starting in A. Our terminal object has arrows going down. This universal cone, let's call it alpha. And from, maybe not alpha, let's call it psi. And from A, if we will draw arrows to the base f of j, it's another cone alpha. Then, since it's a terminal object, there is always a morphism from cone alpha to cone psi. And this morphism is unique by the fact that it's terminal object. And this is precisely our map, some h. Only one. Okay. So that's why it's, as I said, the closed cone. Another way to see the same situation comes from representable functors. And this is the most functorial way. So we will say that a limit is an object that represents cone function. So I am writing a statement that A comma lim F is isomorphic to the set of natural transformations from J to A from functor delta sub A. Okay. How we can see this isomorphism is that if we have any cone, it gives us this factoring map H. This will get here. Conversely, if we have a map from A to lim F, H, we can compose it with cone psi and get alpha. This is a bijection because this is a unique map. What does it mean? That this function is represented. So this is a functor which takes as an input functor f and gives us a set of all cones. Okay. Then here is a fixed object. So you can represent for a given functor f this thing when you vary your a as a contravariant functor where a second component is fixed. So if you will clear here a, it will be a functor, contravariant functor from a to z, and this contravariant functor is representable and represented by lim f. So j comma a of delta blank comma f isomorphic to a blank comma. That's a superpower of representable functor. Everything that gets through some universal constructions can be tied to representable functors. They are precisely the projective object. Maybe later we will see this in a functor category. That's why the solve so important. Well, also what we can derive from this statement is a junction. So that's pretty much clear that we have functor lim and functor delta. So we have delta going from A to functor category J8, and in other direction is going lim. So this is a covariant delta. I will emphasize that it's all true since we assumed in the beginning that J is small. So this is functor category is really a category, and we have a junction. If such limit exists for every functor. Okay, so whenever it exists, then we have a junction. So in case when all limits exist, we have a junction between category and diagrams in the category. Okay. Then, what is the co-unit of this adjunction? Co-unit, as you remember, is from LR to identity. So LR epsilon to identity. So in our case, left is delta, right is lim. So it will be first going lim to A and back. So we are starting from a functor category. Therefore, we will have a natural transformation delta sub lim f to not natural, it's already morphic to f. But yeah, it will be actual natural transformation because these are objects in functor K. Okay. And how this natural transformation will be called? Which letter on the board I haven't used yet? Psi, it's a universal code. Natural transformation from delta subsample to F are codes. And natural transformation with the tip at the limit, it's a universal code. Terminal object. Here. And here is psi. So this is a statement number 1. This is a statement number 2. That delta and limit are adjoint whenever limit exists, and co-units of these adjunctions are universal codes. Nice. Okay, then let's play a little similar but a little different game. And look at the diagram. I will write it again here. A going to f x. Here let's f y. Here f. Here is alpha x. Here is alpha y. Okay. Let's look at this diagram a little different. Oh. Our f of f brings every alpha x to alpha y. Okay. So f of f composed with alpha x is alpha y. But we remember that composition on the left is given by the application of representable function. So it will be f of f star applied to alpha x gives us alpha y. From where to where goes f of f star? Okay. It goes from a morphism set from A to fx to a morphism set from A to fy. Nice. And now this equation we can write in the following way: that from a one-point set singleton, we are picking up morphism alpha sub x. From another singleton, or the same singleton actually, we are picking up alpha a to fy. Here acts our f of f star. And here is equality. So finally, what did we get? This is a functor this is a functor. This is a result of one point. This is also a result of a certain functor. So here we were taking objects of J. And here, for any object of J, we are getting star. So 1.7. Let's think more about it.
So what are we trying to show here?
We are trying to go not from the fact that alpha is a natural transformation, but from the fact that f of f is an application of a functor. So we are trying to just to play a little and see this differently. that our f of f brings alpha x to alpha y. So it moves the cone. Before we were thinking about that cone is just arrows to the diagram that makes everything commute in triangles. Here right now we think that if we have arrows down, who makes them commute? So you can always push down a bunch of arrows, but then there are some certain, let's call them rods, right, on this map, which is called f of j, that should go precisely through the all points where we reached from our goal. That's what we are trying to do right now. I would say that not dual, but a joint way. And in a certain way, joint once you will learn how using adjunctions and can extensions, we can move from that definition to the other one. But right now, we just have this diagram. So I will write immediately you an answer, and then we'll see. No, not A. Here should be J. So I will take J to A, and then this is a function f. Then we will go down and apply function representative function. From the other side, from J, we will go to a singleton, and singleton, to trivial category, sorry, x up singleton. This is the function. And psi, sorry, not psi, alpha, is a natural transformation.
But you're not given that the outside commutes, right?
So this diagram commutes. This diagram does not commute. It's filled with a two cell.
The outer diagram, does it commute?
Which one? This one?
The outer rectangle,
No.
right? Yeah.
It's so we have a function alpha is a composition of this. From this composition goes to this composition.
Yeah.
That's what I'm trying to do. So my alpha, so notation. Notation, this composition of singleton, composition unique map will be called now just one. I picked up 1 point set. It's a functor from category J to set. Let's call it 1. So alpha is from 1 to such function. So this functor for every x gives an arrow from A to f of x. So it's pretty much one leg of legs of cone. So cone consists of legs going down. When we will take this alpha for every object of J, it will give us the whole cone. So the whole cone will be encoded also by this, alpha, but when it's written in this way. Before, I used alpha as a map from delta A to F. Right now, I got rid of delta and A. I got here only trivial function. So all the weight was lifted from here and put here. Yes, it's a junction of common extension. Once we'll see. So I get this. And the result is the following. Statement number 3. we have again such isomorphism. These are all cones over F. It's a functor of A, and this functor is representable by lim F again. Of course, it's isomorphic to this guy. So this way or that way. I will even write this as cones all over F with tip A. I even will write all cones. Questions? Peter, you're looking so sharp there.
No, but
You're okay, or you have questions?
no.
Really?
Good.
Okay. Sean. Cheyenne. Okay. Don't be afraid to ask. Even, yeah, I know that's not so easy. So this thing is a baby stuff. You can see this in any category theory book, in Wikipedia and lab, wherever you. This is a baby thing. But to bring representables and bring natural transformations, I need to go to this isomorphism and this. It takes a little time to think about that. But later, once you will try to work with certain limits, co-limits, you will need like to unpack the thing. So for instance, what if you have a map from some object to some limit of some diagram? Then you want to see what's going on object-wise. You'll get here. If you want to see what's going on cone-wise, you'll get here. So this is a way of certain yoga, certain juggling between these objects. That's what I do, and that's how I get my results. I just know the junctions, and I use the junctions to pass things around. That's how I get like everything in my dissertation.
So the one there that you've written, that's just the constant functor one, is it?
Constant functor from your category given J to set. Constant functor is big simple.
So you just meant to reform, I mean,
I
I guess
reformulate.
I guess what I don't quite see is the point in doing this, because just by that second statement itself, you realize the limit as a representative functor, right? Then what exactly?
Because this one, yes, I changed it, but this from 1 to the picks up a cone with a tip A. So here, if I will want to pick up cylinder, I will change this one to 1, and it will be picking up something there what I need. So these are legs of cone. Here I have the whole cone, and here I'm getting cone leg-wise.
But it hasn't. I just have a feeling that it's also got something to do with the fact that you've changed the target category to set, and you somehow want to.
And this category is complete and co-complete.
Yeah, is that the reason why?
No,
we want to somehow calculate limits there and then.
Well, yes and no. So yes, because limits I can calculate by Ken extensions, and when they arise as sometimes point-wise Ken extensions and using limits for limits, so we get complete co-complete. That's from one side. But the main problem is that when we are going to enriched category theory, we don't have any more picking up a singleton because it has no sense. And we still want to have limits and co-limits. Then we need to change this one by a certain so-called weight function. And now I'm working with cones. Cones have tip. If I will be working with something else, this tip can be like a big circle. You will have cylinder, and you will be picking up the minimal cylinder over your diagram. And this one functors from 1 there, picks up just only one leg. And these legs are arranged together because they started from A. If it will be certain other functor, it will pick a couple legs. And then it will be assembled in certain different ways. And you can assemble the cylinder. Here you can assemble only a cone because you're using a constant functor. When we will go next lecture, or when we will get to that point, to enrich categories, you will never have a constant functor anymore, in general. In certain cases, you will, but only in very particular cases. So constant functor is a blessing. This says as empty set, it's a blessing of set. In general, when you will be working with certain contexts, you don't have it. For instance, when you go to chain complexes, you don't have empty complex, right? Well, you have certain complex with which you can tender it will give you the same. When you're going to abelian groups, when you're going to simplicial sets, you still don't have it. Maybe do simplicial sets have, but if you go to, I don't know, you can imagine different math settings where there is no notion of empty. Like you can have a group on empty set. It has always identity. And so on. Okay. More questions, please. Like, I mean, this is one of the cornerstones of the course. Like this formula. That's fine formula. That formula I can find many places. This, not in many places. Okay. And then to scare you a little more, let's write a functor for co-limit. So for co-limits, all the story need to be, how I would say, turned around. Okay. For co-limit, you should everything turn around. So the cones become co-cones, going down, and the minimal from the bottom is a co-cone. So co-cones are initial in category F, comma delta. Not delta F, but F delta. Because you are going from F to constant factor delta. So here, this will switch and they will switch. But what will be going here? Well, and for this, I will have it. So statement number 4, it's A. Holding F, comma A, isomorphic to GO. Set from 1 to sorry, AF blank sub A. When I was writing delta sub F, I had cones. When I was writing F, comma delta, I had cocones. When I'm writing F1, comma F2, it's a comma category. Comma category is contravariant on the first argument and covariant on the second argument. So when you are looking for cones and change in F, that's covariant change. When you are looking at cocones and change in F, it's a contravariant change using natural transformation from F1 to F2. When you are going to cocones here, all your cones are starting from F of J, and your start of your map is always contravariant because you change it contravariant. Not along the map, but against the map. So that's why I'm getting here this functor. So from F to A, it's a leg of cocone, this guy. So it has F on the first place. So it changed contravariant. If the first picture was this, then the second picture is the following. I will have G of okay, of set it's again singleton, it's again unique, it's F of, and here's A sub A. Of course, I won't be writing here when I put in here F of because it will be too much. But when we are actually going, we're going from G of to A of using opposite factor of F, and then applying contravariant representable function to set.
Oh, you mean to say, to be more precise, we should just write F of instead of F?
Yeah, I have a right to F of, but since I know that this component is contravariant to of, it's a little abuse of notation, but still. So every time you are thinking about that, you have A of F x comma A, you should know that this is A comma blank A composition F of X of. When you will start writing these things down, the category theory will become easier. Before that, you'll have insane number of mistakes. Got it from my own experience. Because this is contravariant score. And you can't put there covariance. You need to get through the O. And when we will be doing n extensions, we will be juggling this thing, like this post composition, to some other place, to the left or to the right. And it will be F of going there, but not F. Otherwise, you will get completely wrong result. I had so many blisters on these things. Just trust me. This is, if you are going to do something with like factorial, thinking that this thing will really save you a lot of energy. Maybe more than everything else what I told today. Well, and to make things a little spicy, I believe they are already so spicy, but I want to make them even more. I will say that there is a theory that tells that the limit of a function f of h category of set can be computed as connected components of category of elements of this function. Or simply speaking, Colin equals phi 0 composition L. Don't ask me what's going on for limits. I still don't know.
What do you mean by connected components? Apparently.
So phi 0 is taking your category, like category C, to set. And the join to discrete function. Connected component of a category is a, so if you have this in the category C, who are your connected components? 1, 2, 3, 4, 5. Two objects are said to be connected if there is a mixed path between them. So paths in the underlying graph without arrows. So you can go a long arrow for it. So all objects here are getting equivalent under this equivalence relation. So if there is a zigzag between two objects, then they are connected. Like this object and this are connected. Yeah, because it's connected this way and that connected that way, and every path is allowed. You can't connect objects from 1 to object of 3. Object in 3 is sitting alone. So path connected components, it's when you are taking small category, it's a set of equivalence classes or objects under the relation that two objects are equivalent, if and only if there is a mixed path between them, or I would say zigzag between them, or they are connected in the underlying graph. If you will use a forgetful factor from a category of small categories to category of graphs. Blah, 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 blah. And many equivalent ways to see.
What was L? Sorry, yeah.
L, category of elements. Category of elements you are taking. So I will remind that L of set has objects. So what are the objects? You have singleton picking up X in F of A. And here you have singleton. So we find them A to A prime here. So X prime to X prime. Here is F, here is F of F. Okay, such form of it. So it's a category of object in which we pick up a distinguished point, but not just objects, A, but images or under the function F, which are sets. So this is a category of elements. This is as I was telling you that when you realize in category of small categories cat, and we have a graph deconstruction, and it's when like it's a new category where we will take all layers to the one level. In algebraic geometry, it's called Etel space. All fibers are getting on the same level. Here it's similar story, but in set. So we assume that here this diagram commutes. If this diagram does not commute, but here is arrow, and these are categories, these are functions. This is a two cell. That's called growth indicator. Growth construction. So when it's not commute, but there are certain shifts. Okay, now let's go to so-called bookkeeping. And for the sake of completeness, I need to introduce very many straightforward notions and just write them all down what is what. So what is the time? We have 25 more minutes. I don't think that we'll today get to friends, but I hope we will get everything. So next topic is complete. Or co, again, in parentheses, complete. Well, here will be just a bunch of statements and definitions. I will write them all down in one column. First, limits in CO are completely the same as the limits in C. Okay. By limits in CO, I mean the functors that are landing from category J in CO. That's what it is. Hence, you can't put here set O, because for set O, you don't have category of elements construction. Okay. Opposite of category of sets is ugly category. Very ugly. It's also category, it's very ugly. So you can't use so straightforward that one. But you always can think about limits in CO as co-limited. Second. F from category A to category B is continuous if for every small category A and for every diagram K from J to A, we have that limit of Fk over J. Sometimes we can write over what category we are taking that, okay? Limit over J of Fk to and natural universal cone beta, it is the same as F of limit over J of diagram K and its universal cone L. So here is universal cone of Fk. Here is universal cone of K. So the factor is continuous if and only if it preserves limit. So just very simply speaking. So f of limit is limit of f, period. That's continuous function. It's the same as why it's called continuous, because we have it in usual analysis. Okay. Then third. Then category A is complete or co-complete. Here you can also write continuous and co-continuous. Here also you can write limit in parentheses following. It means that has limits of all small diagrams. It has co-limits of all small diagrams. Just a name for completeness. When all limits are possible to compute in a category, it's a property of the category, and it's called completeness of all completeness. Next, that it's called the co-limit in functor categories. Are computed pointwise. Are computed point. So, if category B is complete, from this follows that A to B functor category is also complete whenever it exists. So functor category, of course, exists when A is small, but sometimes it exists for A not small, depends. So if B is co-complete, then from A to B is also co-complete. And limits are computed pointwise, as I said. Then, well, before we saw different stuff that was pullbacks, pushouts, products, co-products, equalizers, co-equalizers. Let's bring them all back. Okay. Now you know that the first column that I was writing was co-limits, left column last time, and right column it was there were limits. So what does it mean to be complete? So complete, it is the same as arbitrary product plus equalizers. co-complete equals arbitrary co-product plus co-equalizer. Arbitrary, not binary, not finite. Arbitrary. Well, if binary is finite by induction, but not less than. So it's, you can say if you have finite products, then you will have all products. So, for instance, think about category of finite abelian groups. You have finite abelian groups, that's a category. You can take infinite products because it will be infinite, but it has finite products. Okay, so it's not complete. Okay, but parallel to that, we can split equalizer and co-equalizer also. So equalizer is a product plus pullback, and co-equalizer equals co-product plus push out. So there is an equalizer if and only if there is a product and pullback, and vice versa. So every diagram for equalizer can be made in a pullback diagram, and we will use product. Same for co-equalizer. Hence, you can put instead of X here, and you will have the complete. It has all products and pullbacks. By pullbacks, I mean finite pullbacks of like 2 legs.
When you said equalizers, do you mean finite products or
finite or binary, doesn't matter.
okay.
When I write arbitrary, it's arbitrary. When I without arbitrary, that means just finite. So X cross Y. Here X for product Y. And push out. So you can check something on co-completeness. It will be very often in your life if you are going to be a mathematician, that you will be trying to think, can I take the limits of the limits in certain category? And for that, you will be checking whether this category has products, co-products, equalizers, co-equalizers, pullbacks, push out. You do not need to check every single diagram. This is a shortcut. Because checking every single diagram or going through these adjunctions, this is suicide. Much simpler. Does it have product? Does it have equalizer? If only finite, then it's called finitely co-complete. So in certain cases, you don't need all limits. You need only finite limits. So category has finite limits. So co-limits is called finitely complete. And for this thing, you need only finite products and co-products. Okay. Then theorem.
No, sorry, do you mean to say if you have finite products and equalizers, then what do you say? Finite products.
It will have finite limits. So limits of a finite diagrams.
Okay.
So your J will be finite category, not small, but finite. So it has finite number of objects. So you can draw it. Here. Every time I'm writing factor L, it's supposed to be left adjoint and R right adjoint. So if L and R are adjoint, then this function L is co-continuous, right is continuous. So to check factor whether it's continuous, it's straightforward when it has adjoint. So it was 6.7. It's called again theorem. Well, it's partial as previous one. it's called home, preserves, limits, involves, where both with a star. So it's like when you assign some contract, there are also some special conditions. So both, just we need to think a little what mean both verbs. So if x capital from J to category A is a function, okay, why f is a function, then if there exists limits of f over J, then a comma limit of f sub J over J is isomorphic to limit over J will be a f of J. Where here by f of J I am emphasizing how my functor acts on objects J small of category J. Second, if there exists co-limit of functor f over J, then a of co-limit over J of f comma a is the same as limit over J of a, here f sub J, fj comma a. Again, limits are going out from covariant component, and co-limits are converted into limits on a contravariant component. Okay. There are two problems immediately. Co-limit I can take from covariant variable, and limit I can take from contravariant variable. Immediately. This also is connected with notion of flatness of functors and so on. So in general, I can take co-limit from a second component here. Okay. If I could, that means that co-limit has left adjoint. So, but co-limit it has right, not necessarily has left adjoint. So it's a complicated story. Okay. Then not much left. It's Fubini theorem and examples. Of course, how will we proceed with limits or co-limits if we don't know how to like compute repeated limits of co-limit. So repeated limit of co-limit is a limit or co-limit itself. Yes, it is. And this is called Fubini theorem. As for integration, we'll have it many times. And how many times we will use it, I can tell explain. So from some point it becomes so natural that Fubini theorem exists that you will completely forgetting to check. It's much easier than an analysis, but still. So theorem Fubini. So suppose A cross A prime B is the function. And A prime and A are small. So you have a diagram, double index diagram. Okay. The diagram where all the vertices has two indexes. And A prime. And B has co in parentheses and limit of shape A, comma, and A prime. So every limit or co-limit over A exists, and every limit or co-limit over A prime exists. I mean, co or limit depends which statement we will pick up, because there's Fubini for limits and Fubini for co-limits. Then co-limit of over A cross A prime of F equals, what equals, sorry, isomorphic. So co-limit of co-limit of F computed over A prime over A isomorphic to co-limit A prime of co-limit over A of F. Or in other way, it's that whether one of these guys exists all other. That's a Fubini. Now example. First, by complete categories. So categories by complete. Let's write down. So by complete means complete plus co-complete. Okay, by complete category. Has topological spaces, groups, building groups, rings, are modules, category of small categories, compact house door spaces, simplicial sets. Later you'll see that these categories possess certain bifunctors that remind tensor product, and this bifunctors has adjoint, and they will be called cosmoi or entangled cosmos. So it's a paradise where every object lives when you are working. Then finite by complete categories. Finite sets, finite abelian groups, finite dimensional vector spaces, and any abelian category. What is a kernel? Kernel of a map F is a pullback of F and zero map. What is a co-kernel? It's a push out of map F and zero map. Abelian category has by product. So objects which we write as direct sum that are finite products and finite co-products, and they are isomorphic, they call them finite pi products. So it has all finite products and finite co-products. It has equalizers and co-equalizers, because equalizer of two maps is a equalizer of two maps is the kernel of their difference. And Co-Equalizer is I forgot what. So, any appealing category has all pullbacks, pushouts, finite products, co-products, equalizers, co-equalizers, but it does not necessarily have finite, infinite products or infinite co-products. When it has, it becomes complete by complete, but not necessary. R modules is a billion category. It has, but not necessary everything. Okay, couple more. 5 minutes we have. Then other. Some other important statements. So complete lattices. Complete lattices. They are complete, but not complete. What is a complete lattice? It's a lattice where every subset has meet and join. They are complete, but complete not is inside. So when you are taking limit of lattices, it's not limit inside the lattice. It's a limit of the spaces that are really lattice. So this category is complete, but it's not complete. So the name complete lattices is referred to lattices, but not to completeness of category of lattice. Okay, that's a little confusing, but it is. So metric space. Metric spaces and continuous maps between them. Categories finite. Finite. And baby example. Poset. So partially ordered set as a small category is bicomplete if and only if it is a complete lattice. So it's a lattice plus has all meets and all joins. So you can take any partial ordered set, consider it as a category, and then think whether I have limits in my baby example. I have it when this category, when this poset is actually a complete lattice, because all meets and all joins. So, what?
So what are you saying about metric spaces? That category is what?
This one?
No metric spaces.
This finitely complete. So it has finite.
What about co-complete? What about co-complete?
I don't know. Think so. Okay. And to finish, I want to ask the question that I was assuming that someone will ask, but nobody asked me. Can I change limits and co-limits? That's a very serious question. Who studied game theory? No, no. When you have function of two variables, okay, when you have function of two variables, so let's f of x and y, f of x and y, then I can take the maximum over x is greater or equal than minimum over x. Okay. But then, when I will take maximum over y, it's already bounded by this guy. Then it gets fixed. It's now a number. Then for every y, I can take minimum with respect to y. And minimum is bounded below by the sum. This called is maxi-min less or equals than minimax. This is a general method. Maxi-min is less or equals than minimax. Less or equal an arrow in that direction. So who is maximum, who is minimum? Limit or colimit? I can exchange
Yeah, that makes sense.
limit and colimit and comparison. And for certain cases of A or A prime, don't remember exactly, there is a model. Only for certain. Unfortunately, I can exchange so easy. The same is here. When you, if you want to check it, take a rectangular any matrix with integers or reals and compute maximum by columns and minimum between them. Minimum by rows and maximum between them. You'll get this. It's a game theory, mathematical economics, operation research. One of the fundamental, not principle, but rules you always have. Like Nash equilibrium, so on, uses a lot. But it has very simple statement, which was known probably, I don't know in which century, if you count numbers and tables by minimum by columns, and so on, like, can you exchange it or not? So you have this saddle point, and they not concept. This has precisely counterpart in category theory. About limits and colimits. Well, we finished finally today limits and colimits. We are again one lecture behind. So I was going to start today ends and coins, but unfortunately I can't do this. I want to say everyone thank you for participation. If the record is not well, then yeah, today was not the best day for recording. And thank you again. If you have any questions, please ask me anytime.